So let's start from the point we had left off. Uh, we are trying to solve this equation. We realize that this equation is neither linear nor separable or homogeneous. So we wonder if it is exact. To check that, we look for a function psi xy whose x derivative is m and y derivative is n. Let's see if such function exists. Well, let's start from this equation. So I am looking for a function whose x derivative is 2x plus y squared. Well, so this function should be what? Integral of this with respect to x, and that's nothing but x squared plus x times y squared plus a constant, of course. But here, this is a function of two variables, and I am taking derivative and integrate with respect to x. Therefore, I consider y as a constant. Therefore, here the constant term may include y in it. So I should write something like this, hy. Okay. And what is this hy? Well, I will determine hy using this equation. Why is that? Because you see, I have psi xy is equal to this. Therefore, its y derivative is equal to what? Is 0 plus 2xy plus h prime of y. And this should be equal to 2xy. So from this we get what? 2xy plus h prime y is equal to psi sub y, but that's equal to n, and that is 2xy. And from this we see that the one variable function h is derivative 0. Now h is a function of a single variable, which is y, and its derivative is 0. Therefore, this hy is really a constant, okay? Hence uh, this psi xy is what? It is x squared plus x times y squared plus hy, and hy is just a constant. So I really found a function psi xy so that its x derivative is m, y derivative is n. Hence, so that the equation is exact. Well, if the equation is exact, then we know that the solution of the equation is given like this, right? So if the equation is exact, then the solution is given like this. Therefore, my in my example, the solution will be what? Let's see. In particular, the solution, I should say maybe general solution, is what? Psi xy equals c, right? Well, here, of course, this c and this c are not the same, right? I should differentiate the two, so I should write it this way. This implies what? The solution is equal to x squared plus x times y squared plus c equals c prime. But c and c prime are both arbitrary constants. Therefore, I can just write this, like this. Double prime maybe, but well, let's just make it c. So this is my solution, and here c is any constant. So this is the solution, okay? In this example, actually one may solve y for x, right? This is not difficult. You have to just take a square root. But you will have plus minus square roots. And which one you will choose? Well, you will choose, of course, depending on the initial condition if you are given. Therefore, since no initial condition is given, you may just leave it like this. Okay. All right. uh, okay. Now we have a criteria to check whether equation is exact or not, right? If it is exact, then life is easy, but otherwise things might be difficult. Uh, so question is how to check whether an equation is exact or not. All right. Now, if it is exact, you see, I have this, right? This is my equation. And if it is exact, then there is psi of xy with x derivative is equal to m and y derivative is equal to n. Of course, if these functions are continuous and differentiable, then I can take further derivatives if m and n are differentiable. Then actually continuously differentiable, then I can take further derivative, and y derivative of this would be just m sub y, and x derivative of this gadget would be n sub x. And if, as I said, m and n are continuously differentiable, then this function and this function would be continuous. And in that case, we know that these two expressions are the same, right? You may change the order of differentiation, and taking derivative with respect to x and then y is the same as taking derivative with respect to y and then x. So this implies, hence, we get what? M sub y, which is psi xy, but this is equal to psi yx, and that's equal to n sub x. So if an equation is exact and if the coefficient functions are continuously differentiable, then I have this. So if m sub y is not equal to n sub x, then there is no way this equation will be exact. Okay. Thus, if m sub y is not equal to n sub x, then the equation cannot be exact. And you wonder, if it becomes exact, if these partial derivatives are the same. this question is answered in the following theorem. Let me just write down the theorem. Or maybe before this theorem, let me do one example related to this criteria. For example, let's uh, uh, okay, decide if the equation, which equation, let's say 2xy plus x plus y dy dx is exact. Well, uh, okay, what is xy? It is just 2xy, and nxy is just x plus y. For this to be exact, m sub y should be equal to n sub x. What is m sub y? Well, it is just 2x. And what is n sub x? It is just 1. And these functions are not the same since m sub y as a function is not equal to n sub x as functions. The equation is not exact. Okay. All right. So the next question is, if they were exact, the same, would it be exact? And that is answered in the following theorem. Okay, so let n sub y, m sub y, and n sub x. So these are continuous. In particular, m and n have continuous partial derivatives. Continuous in the rectangle. In the rectangle R, in some rectangle R, specified by these conditions. So x ranges between alpha and beta, y ranges between gamma and delta. Then the equation mxy plus nxy dy dx equals 0 is exact if and only if uh, n sub x or m sub y equals n sub x on R. Okay. I will not talk about the proof of this, but it is basically actually integration, nothing else. Maybe a sketch of proof. Sorry. All right. So we are given that m sub y equals n sub x on R, right? What is R? R is a rectangle. Actually, you don't need a rectangle. It's enough if R is simply connected. Okay, so suppose that the important thing is that there should be no holes in the region. Okay, no holes in the region. Just take a point here, x0, y0. Okay, and then for any point xy, we define our function sin xy as follows. This is just the path integral. Just choose any path. Okay, just choose any path. Let's say gamma from x0 to y0, and integrate uh, what? Okay. Bir dakika, ne istiyorum ben? Bunun okay. Yeah, okay. Yeah. Okay. So this is a integral, a path integral. You wonder why this is well defined, right? I mean, why this value is well defined? Because you just take any path joining these 2 points, but somebody else could uh, equally choose another path like this one. Okay, let's say tilde, and use this path to compute the value of the function. So if I write gamma tilde here, would it, give us the same answer? If I get a different value, then this function wouldn't be well defined, because depending on the choice of the path, you get different answers. So which one should we take? The important thing is the following. By the assumption m sub y is equal to n sub x, and therefore this integral is path independent. Okay, this function is defined since uh, the integral okay was m sub y equals n sub x, so that the integral is path independent. Okay, I guess you have seen this in 252, right? Advanced calculus. Since these are the same, m sub y is equal to n sub x. This is a path independent integral, and therefore it doesn't matter which path you choose. And then you do what? So I found a function psi xy. Then one has to prove the following: must check what? X derivative of this is equal to m, and y derivative of this is equal to n. Well, let me also talk about this, why this is the case. Well, let's write down our definition again. So this is mxy dx plus nxy dy. All right. I know that this integral is path independent, right? So in my rectangle, I do the following. Suppose this is the point x comma y, and this is x0, y0, and I would like to take the partial derivative of this with respect to x, right? I would like to compute this gadget. How can I compute this? Well, this is at xy. This is equal to the following. You take the limit as h goes to 0, psi x plus h y minus xy uh, okay, so I have to take this limit. Well, x plus h comma y is somewhere here, and I uh, go like this. I go up here and then go like this. Okay, I can choose any path I want. Okay, so this is my gamma, and this part, let's say, uh, okay, this part, let's say gamma h, okay, the small part. So let's see how things work. Okay, now this is limit as h goes to 0, psi x plus h comma y. So this is just integral from so this is integral along gamma and gamma h. Let me write this way, and then I have m, şöyle isterseniz biraz daha aşağı yazayım, xy limit as h goes to 0, okay, psi x plus h comma y. So it is this point, and I come to this point by following gamma first and then gamma plus gamma h. So this is integral from along gamma and gamma h, m dx plus n dy minus integral. So here this is just psi xy. Psi xy is just so the value of the function at this point. So this is the integral along gamma m dx plus n dy and divided by h. Well, you see, this is integral first along gamma and then plus along gamma h. But I subtract the integral along gamma, so they will cancel each other. So this integral will be cancelled with this one. Okay, so what is left? What is left is just the following. Integral along gamma h of m dx plus n dy divided by h. All right, what is gamma h? Gamma h is the following path. If I parameterize gamma h, y coordinate is constant, it is y, and x coordinate is just x plus t. So I can write it this way, x plus t, and y coordinate is constant. Now what is then d? So this is the x coordinate plus. Okay, so x t is just x comma t. Well, here, sorry for the notation. I mean the x coordinate of this parameterization. Okay, and the y coordinate of this parameterization is just y. So what is dx? I take derivative with respect to t, of course. Dx over dt, it is just dt. What is dy over dt? It is just 0. Okay. So y coordinate doesn't change, and x coordinate changes by t. So dx over dt is 1, dy over dt is 0. So if I plug all this into this limit, let's see what we get. Okay, here's parameterization from t ranges from 0 up to h, 0 up to h, and then inside m I have x, y. X is just x comma t, y is just y, and dx is just dt plus and dy. Dy is 0, so that's it. Divided by h. All right. Well, you let h go to 0, but you see, what is this gadget? This is just, I can write it this way. Okay, so if, okay, şöyle diyeyim. Uh, okay. If let's say m tilde xy, here only you see t is the variable, right? And t is an antiderivative for m x plus t comma y with respect to t. What I mean is this: t derivative of this is just x plus t comma y, right? I just integrate with respect to t. Then of course this expression becomes what? This is limit as h goes to 0. What is this integral? How would you take the integral? You just compute an antiderivative, which is m tilde, and compute this at the endpoints at h, and then at 0, and divide by h. But what is this? This is nothing but the definition of derivative. So this is just m prime, m tilde prime at 0. What is m tilde prime? It is just m x plus h comma y at h equals 0. Well, that is just mxy. So what we have seen is then, hence psi of xy is just equal to mxy. Okay. Similarly, one can show that the y derivative of this is just nxy. Okay. Right. computed the y derivative, the x derivative, and it turned out that that's equal to m. Similarly, you compute the other derivative and you get this. Hence, thus the equation is exact. Okay, so we proved the theorem. Then the important thing is, of course, that these two partial derivatives are the same, and this gives me the fact that this integral is path independent. Okay. Okay. Once it is path independent, then I can choose the path any way I like to compute the partial derivatives, and I choose it this way, and that gives me the result I am after. Okay, so any questions so far? This is basically advanced calculus. You have seen actually most of this in advanced calculus. Just a simple application of that. Okay. So to check whether an equation is exact or not, it is enough to check that partial derivatives are equal to each other or not, right? M sub y should be equal to n sub x, but your region also has to be a rectangle or simply connected. Maybe I should write as a remark. The region R in the theorem, in the statement of the theorem, could be replaced by any simply connected region. So it doesn't have to be a rectangle, okay? However, if it is not simply connected, then the theorem fails. On the other hand, the theorem fails if R is not simply connected. Let me give you a quick example. Okay, so for example, region, okay, let theta to be this function, xy. So this is, let's say, arc tangent y over x, okay? And if you take differential of this, you will get something like this. Y dx minus x dy divided by x squared plus y squared. Aslında çok emin değilim. Bakalım, bunun x'e göre türevini alırsam, içinin x'e göre bunun türevi 1 artı 1 bölü y bölü x'in karesi çarpı içinin x'e göre türevi, o da eksi y bölü x kare. Buradan da ne çıkar? X kare gelecek, x kare gidecek. Eksi y bölü x kare artı y kare dx olacak. Pek de öyle olmadı, değil mi? O zaman şöyle. Şimdi bunun x'e göre türevini aldığım zaman 1 bölü 1 artı y bölü x'in karesi çarpı içinin türevi, o da bu çıkıyor. Yani o zaman şöyle. belki bu artı bu eksi. Y dx minus x dy olacak. Okey. Yok. Tamam. Y dx. X dy minus y dx. Okay. So if you look at this one form, and if you consider this equation, so let's take m equals mxy, which is minus y over x squared plus y squared, and xy is equal to x over x squared plus y squared. Okay, so the equation mxy plus nxy dy dx is what? This equation is the following. Then okay, şöyle yazabilirim. Eksiyle çarptığımı düşünün. Eksi x kare artı y kare dy dx equals 0. So this equation is defined everywhere on the plane except the origin, right? So note that this equation is defined on R2 minus the origin, because at the origin the coefficient functions are not defined. And what is the solution of this? This is almost an exact equation. If you integrate this, you will get what? You will get this function theta. Okay. Integrating this equation, so assuming it is exact, you try to solve it. One gets the solution theta xy, which is tangent inverse y over x equals c. Okay, you get this equation because integral of this expression is tangent inverse y over x. Okay, so we get this solution, and c is any real number, but you see that the solution is not defined on the y-axis, although the equation is defined everywhere except the origin. Okay, it is defined everywhere except the origin. The only trouble point is the origin, but you look at the solution, and solution is not defined on the y-axis where x is 0. So solution is not defined. Theta is not defined on the y-axis because x is 0 there. Therefore, you don't get a solution defined on the whole R2 minus 0. And this is not a surprise. So, hence, we don't get a solution on R2 minus 0, 0. So we wonder whether the theorem is not correct or not. Well, theorem is correct, but the hypothesis of the theorem is not satisfied. The region is not simply connected. The theorem doesn't apply here since the region R2 minus 0, 0 is not simply connected. Yani R2'den bir nokta çıkartırsanız o region artık simply connected değil. Simply connected değil ne demek? Simply connected değil demek şu. Verilen iki tane noktayı birbirine bağlayabiliyorsanız o connected. So if you can join any two points on a region by a path, it means it is connected. But if there are different ways of connecting different points, then the region is not simply connected. For example, I can join these 2 points this way or this way, and these paths are essentially different. I cannot deform this path to this path, because if you try to do so, you have to pass through the origin, but origin is not in your domain. Therefore, there are essentially more than one ways of connecting these 2 points. Therefore, it is not simply connected. Simply connected means there's essentially a unique way of connecting these 2 points. In this case, you see all these paths can be deformed into this line segment. This means that there's essentially a unique way of connecting these 2 points. But here it is not the case. Okay, that's why it's not simply connected. Going from one point to another using different paths gives us different results. Okay, and in the case of this theta function, what happens is the following. If you take different paths and integrate this, you get different results. If you go this way, you get, let's say, minus pi, but if you go this way, you get plus pi. And if you go like this, to this point, you will get, let's say, 3 pi plus, no, pi plus, let's say, 4 pi, right? You go halfway and then 2 more times, so you get 5 pi. So integral of this expression from this point to this point, depending on the curve, gives you different results because you measure the angle. If you go like this, it is pi, but if you go like this, it is minus pi. Or you may go like this, and it will be, let's say, 5 pi, and so on. Okay, so that's why the argument we have given above doesn't apply to this expression, because the region is not simply connected. All right. Okay, now let's see what's an integrating factor. Suppose we have a differential equation and it is not exact. Suppose that the given equation mxy plus nxy dy dx equals 0 is not exact. So what can we do? Well, we may do something we used to solve linear equations. What was that? We multiplied the equation by some function and it became exact, right? It became an equation that you can integrate. The left-hand side became the derivative of some other function. In this case, we may try to do something, that kind. So, question is, can we find a function like the one in the linear equation case, but this time we ask for this function to be a function of two variables because we are taking derivatives with respect to both variables. Can you find a function mu xy so that after multiplying the equation with mu xy, the equation becomes exact. And you see, if I multiply this equation by a function, equation essentially doesn't change much. If this function has no zeros actually, then it won't change at all because then you can also divide with the same function. So this is a nice idea to try, right? If we can find such a function, then it means you can solve the equation. If such a function exists, then we will call it an integrating factor. If such mu xy exists, then we call it an integrating factor. For the equation. Why integrating factor? Because we factor the equation with that function so that the equation becomes integrable. You can integrate the expression. That's why we call it an integrating factor. So now let's see whether such mu y exists. So what we ask is the following. We want mu xy so that after multiply the equation with this function, the equation becomes exact. So that m xy times mu xy plus n xy times mu xy and then dy dx equals 0 is exact. Okay, right? We have this equation, original equation. I multiply by mu, and I want this equation to be exact now. Well, for this to be exact, of course, we have the following criteria, that the y derivative of this should be the x derivative of this gadget. The y derivative of this should be x derivative of this. Now, if you take derivatives of both sides, you see they are both functions of x and y. So we just apply chain rule. Derivative of this with respect to y is what? M sub y times mu plus m times mu sub y. And this is derivative of this with respect to x, n sub x times mu plus n times mu sub x. Okay, what we have obtained? Well, we have obtained a equation, this time in mu, right? Mu is the function we are looking for, but mu has derivatives with respect to x and y. So this is a partial differential equation in mu. Okay, and partial differential equations probably are difficult than the original equation. So while we are trying to solve an equation, we ended up with another equation which is probably harder to solve. Okay, in the next hour, what we will do, I will, make some simplifications. We will just give some, we'll make some sacrifice, and our equation will be something simpler, and then we will try to solve it. All right, let me stop at this point and start in 10 minutes.